Zeros and Exam 2 review presented by Ms. Shuka, Mr. Carrizales, and Mr. Sassi. This session will be recorded, so now please mute your mic for the best sound experience. Without further ado, here is Ms. Shuka.
Hello, everyone. Happy Friday. So today we're going to be looking at section 2.5, 2.6, which is part of your exam 2 review. So last week we were able to do 2.2, 2.3, and so we'll start with that. So last week we looked at finding or using synthetic division or long division to help us divide two polynomials. But more importantly, we want to use those methods to help us find the zeros. Okay, so if we look at this picture here, it gives us all the zeros. So we have a zero here, a zero here, and a zero here. And so we want to make sure that we can find these points. And so to find those points, we're going to be using different methods. But one of the first things we got to look at is how many of these zeros are going to appear for a polynomial function. So for example, here we have 3, here we have 2, here we have 3. And then some might not be, some might be imaginary zeros as well. Okay, so one of the things that we want to look at is for any polynomial, this theorem tells us that we're going to have, so if you have a polynomial of degree 5, for example, then you're going to have 5 zeros. And some of those zeros are going to be imaginary zeros and some will be real zeros. Okay, so here it says determine the number of zeros of the polynomial function. So to determine the number of zeros, you want to look at the degree of the polynomial. And the degree of the polynomial is the highest, the term with the highest exponent. So in this case, we have an exponent of 3 and an exponent of 2. So 3 is bigger than 2, so we say that the degree is going to be 3. And if we look at the second one, the degree here is going to be 6. So even though it's not listed first, it is the highest power. So we say that the degree is going to be 6. And so the first one, since the degree is 3, that tells us that we're going to have 3 zeros. And if the degree is 6, then we're going to have a total of 6 zeros. Some of the zeros might be repeated, and that's okay. So it says find the zeros of each polynomial function. So throughout the course, we have been looking at different types of polynomials. In the first one, this polynomial is a line. And so if we were to graph it, then we can see that that zero is at 2, 0. And to find the zero, we set the function equal to 0. And then if I add 2, I get that x is equal to 2. But then as we go on, the problems get a little bit harder. So in this second example, we have a quadratic equation. And if we were to graph it, then we can see that the 0 is at 3, 0. But if we saw it algebraically, we let y equal 0. And since it's quadratic, we can either use the quadratic formula or we can try to factor. Not everything factors, so you want to be aware of that. In this situation, or this polynomial, it does factor, so we get x minus 3 times x minus 3. We can set each factor equal to 0 and solve for x, so we get x is equal to 3. Now notice here that the 3 is repeated twice. The degree is 2, that means you should have 2 zeros. And even though they're repeated twice, we do count them as individuals. So we have 1 0 here, and the second 0 is 3. And because they repeat an even number of times, then, sorry, I had to sneeze. So because they repeat an even number of times, then this is why the graph will touch it and turn. If you notice on the first one, it only repeated one time, which is an odd number of times that it repeats, and that's why the graph crosses through the 0. Now if we keep going, now we're going to look at a different polynomial here. if I was to multiply my x's here, I would have x times x is x squared times another x would give me x cubed. So the degree would be 3. That means that I should have 3 zeros. And so if I solve for x here and set each factor equal to 0, then I get x is 0, x is equal to 2i, and x is equal to negative 2i. And so in this example, we have one real number, which is 0, and then we have two imaginary solutions, which are 2i and negative 2i. So for these, since they are imaginary, we don't see them on the graph, but they are counted as the total number of zeros. So what we want to do today is how do we find these zeros? And so some of these questions are going to tell you to find all the zeros, and then they're going to give you at least one zero. And so in this example, they tell us that x is equal to 4 is a zero. Since you know that x equals to 4 is a zero, then we can use synthetic division to find the rest of the zeros. So if we take our polynomial and we have x cubed minus 13x minus 12, if we set up our synthetic division, then we have that x cubed, the coefficient for that is a 1, so I put my 1 here. I don't have an x squared, so I'm going to use a 0. And then for x, I have a negative 13. And then for 12, or my constant is negative 12. 4 is a 0, so I bring that down to use as my k here. I'm going to bring down the 1. So now 4 times 1 is 4. 4 plus 0 is 4. 4 times 4 is 16. Plus negative 13 is 3. 4 times 3 is 12. And if I add, I'm going to get 0. Okay. So why is this important? And how has it helped me find the rest of the zeros? So if we look at the quotient of what's left here, since we started with an x cubed polynomial, now we're going to go 1 degree less. So we're going to take the first number, and that's going to be x squared right here. And then we're going to have our next number, 4, which is going to be, that should be a positive 4x. And then we're going to have our 3. The last number here is going to be a your remainder. Okay. So let me just change that number. Oops. So this right here should be x squared plus 4x and then plus 3. Okay, so if we try to factor, then we get x and x. 3 times 1 is 3. And then I would get a plus and a plus. Okay, so now we would get x plus 3 is equal to 0. And x plus 1 is equal to 0. So my solutions would be x equals negative 3 and x equals negative 1. Okay, so this is incorrect. So your solutions are x equals 3, x equals negative 1. So here, notice that we had a cubic function, and we were able to break it down using synthetic division to something that's quadratic. Once you have it quadratic, then you can use quadratic methods like quadratic formula, factoring, completing the squares, square root property. So there's many different properties that you can see. Now, the next question says, find the zeros of this polynomial. And I have a question here. What is the difference between this example and the previous? And if we go back to the previous, they give you the polynomial, but they tell you that x equals 4 is a 0. In this next problem, they don't tell you that there's a 0 at all. Okay, so what we could do is we could guess at any number and see if it's going to be a 0. But since there's so many numbers, infinite amount, then we don't want to be guessing and then possibly spending too much time. So we do have a theorem that helps us break our list into a smaller workable list. And so this theorem is called the rational zero test. And what it tells us to do is you want to look at the factors of the constant term and then the factors of the leading term. And so just to review, what is a factor? If you have the number 8, the factor is basically any numbers that you can multiply together to give you that 8. So here 1 times 8 will give me an 8. 2 times 4 will give me an 8. So the factors of 8 are 1, 2, 4, and 8. In 24 we have 1 times 24, 2 times 12, 3 times 8, 4 times 6. And so those are going to be your factors. So if we look at this example, my constant term is -9. My leading coefficient is 1. Your leading coefficient is always going to be in front of the highest of the variable with the highest power. So that's why it's 1 for this one. Now what we want to do is we want to find the factors of 9. You could put -9 here or 9. What's going to happen is we're going to use both signs. So the factors of 9 would be 1 times 9 and 3 times 3. So the factors are 1, 3, and 9. Now the leading coefficient is just 1. So the factors of 1 is just going to be 1. And to include, for example, if we had a -1 times a +9, then you get the -9. So to include all the different possibilities, we use the plus and minus for each of those numbers. So I'm going to have ±1, ±3, ±9, divided by ±1. So if we divide, we have 1 divided by 1 is 1. 3 divided by 1 is 3, and 9 divided by 1 is 9. So instead of checking an infinite amount of numbers, we broke our list down to 6 numbers. And so these are possible zeros. And so in order to check them, now we take this list and we use synthetic division with the list. I usually start with a +1. If that doesn't work, then I go to -1 and so on. Okay, so let's go on to the next one. So I'm going to use +1. So I have x cubed, so I have a 1. X squared is a 1, -9, and -9. And so I'm going to check if 1 is a 0. In order for it to be a 0, your remainder has to be 0. Okay, so if I bring down the 1, we get 1 times 1 is 1. 1 plus 1 is 2. 1 times 2 is going to be 2. -9 plus 2 is -7. And -7 times 1 is -7. And if I add it to -9, we get -16. So notice that your remainder here is not 0. That means that x equals 1 is not a 0. So it's okay. Now we just try another number in our list. So we can try -1. And if I do the work, bring the 1 down, multiply it times -1, we get 0. -9 times 0 is -9 times -1 will be a +9. If I add it to -9, I get 0. So now that we have 0 as a remainder, then that's going to be a good thing because now it tells us that x equals -1 is a 0. But more importantly, it helps us to now consider our quotient, which is going to come down to be quadratic. Okay, so we started with x cubed. So this one would be starting with x squared. So we have x squared. There's no x. And then your constant is -9. Since this is quadratic, now you can apply any of the quadratic methods that we have. So I'm going to go ahead and set it equal to 0. I'm going to add 9 on both sides, take the square root, and so I get x is equal to ±3. So my degree was 3, so I have to have 3 zeros. And just to summarize, one of the zeros is x equals -1 that we got from the synthetic division. And the other 2 zeros are -3 and +3. Later in this session, we're going to need the factors. To find the factors, all we have to do is take this -1 to the left side, and we get x plus 1. If we take -3 to the left side, we get x plus 3. And if we take 3 to the left side, we get x minus 3. So later we'll use the factors for something else. So let's try another example. Find the rational zeros of the polynomial function. Enter your answers as a comma separated list. And if it doesn't exist, then we would put does not exist. Okay, so first we need to find some possible zeros. Okay, so to do that, we take our constant, which is 1. The factors of 1 is just 1 times 1. And then the factors of 2 are going to be 1 and 2. So if I set them up, I'm going to divide 1 divided by 1 and 2. And that's going to give me 1 divided by 1 is 1. And 1 divided by 2 is going to be a half. So now I have 4 zeros or possible zeros that I can check. So again, I always like to start with 1. I have a x cubed, I have a leading coefficient of 2. My x squared has a coefficient of 3. I don't have an x, so I put 0. And then my constant is -1. So if we do the work, bring down the 2, 1 times 2 is 2, plus 3 is 5, times 1 is 5, plus 0 is 5. And then 5 times 1 is 5. Added to the -1, we get 4. So that tells me since the remainder is not 0, x equals 1 is not a 0. So I'm going to try -1. And so we bring down the 2. 2 times -1. -2 plus 3 is 1. Times -1 is -1. Plus 0 is -1. Times -1 is +1. Then we get a 0. So that's a good thing that it's 0. That means that x equals -1 is a 0. And now I can take my quotient down here. So I started with x cubed. That means that the 2 is going to be the leading coefficient for x squared plus x minus 1. So now that this is quadratic, then we have some options. We can try to factor. We can try to use the quadratic formula. So this is factorable. 2x squared is 2 times x times x. And then 1 is going to be 1 times 1. And if we do the work, we get 2x minus x is x. So it does factor. Set each factor equal to 0 and solve for x. So here I add the 1 and I get 2x equals 1. Divide by 2. So x is a half. And then the right side we subtract the 1. So we get x equals -1. I should have 3 zeros. So let's write them down. So my first 0 is x equals -1 from the synthetic division. Then we have x equals a half and x equals -1. Okay. And then notice here that the x equals -1 is the same. And so we say it has multiplicity of 2. It repeats an even number of times. So when we graph it, it's going to touch and turn. Okay, so now let's look at this one. This problem has, there's 2 ways you can do it. I'm going to show you both ways. The first way is using what we were doing earlier. If my constant here is 0, then my factor is just 0. And then my leading coefficient is -1. So I just have a 1. So 0 divided by 1 is going to be 0. So that's my possible rational 0. So I'm going to check the 0 and see if it works. Okay, so here I have a 6. So the leading coefficient of T6 is -1. So this would be T to the 5th, T to the 4th, T cubed, T squared, I have a 1, T, and then your constant. So if we do the work, and I bring the -1 down, -1 times 0 is going to be 0. If we add, we get 0, and then that's going to be 0. And we keep going, so this is what's left here. Since your degree was 6, then you're going to start with a degree of 5. Okay, so -1 is going to be -t to the 5th. This would be t to the 4th, t cubed, t squared. So the 1 is going to be a t. and then we have our constant. So to continue, we start the process again. So if you find the possible zeros, it's going to be 0 again. So you have t to the 5th, t to the 4th, t cubed, t squared, t, and then your constant. And if we bring down the -1, then we end up with this information. Since we had a t to the 5th, now we break it down to t to the 4th. And you can keep doing this process over and over. But then I noticed t to the 4th, I can factor that out as -t squared minus 1 times t squared minus 1, set each factor equal to 0, and solve for t. So here we get, we're going to add a 1, divide by negative, so we get t squared equals negative, the square root of -1, which is going to be t equals plus or minus I. And then on the right side, we get plus or minus 1. So your degree here should be 6, or it's 6. So you should have 6 zeros. So 1 0 is 1. Another one is -1. Then you have a positive I, a negative I. Then you have the 0 for this one and the 0 for this one. So that's 6 zeros. So notice that synthetic division can help you here as well. But something I like to tell my students is before using synthetic division, ask yourself, can you factor from the beginning? Because if you can factor from the beginning, then it makes everything a little bit faster, okay? Here's the graph of our zeros. Notice you had 2 zeros. That's why it touches and turns at that point. And then for the 1 and -1, it's just going to cross. The i's are imaginary. That's why we don't see them on the graph. So the second way, without using synthetic division, is notice that in these two terms, they have at least a t squared in common. So we can factor out a t squared. So that will leave me with 1 minus t to the 4th. I can set t squared equal to 0 and 1 minus t to the 4 equal to 0. So 1 minus t to the 4th is going to factor as this, giving us the plus and minus I and the plus and minus 1. And if we solve for t here, we get t equals 0. Since it was squared, that means that there's 2t equals 0s here. And so we get the same answers. Okay, let's try another one here. We have a polynomial with degree of 4. And so we want to find all the zeros. So we do the same idea. The constant is 24. So the numbers that I can multiply to give me 24 are 1 times 24, 2 times 12, 3 times 8, 4 times 6. And then the leading coefficient is 9. So that's going to be 1 times 1 and 3 and 9. Set up our ratio here. So we get all the constant factors divided by the coefficient factors. So we're going to have 1 divided by 1, 2 divided by 1, 3 divided by 1, 4 divided by 1, and so on. And then we're going to have 1 divided by 3, 2 divided by 3, 3 divided by 3, and so on. And then 1 divided by 9, 2 divided by 9, 3 divided by 9, and so on. And so we get a list of possible zeros. If you're trying to input this into WebAssign, just be careful because WebAssign doesn't have the little symbol for plus and minus. So what you need to do is, if it says, usually it tells you to enter from smallest to greatest. So you would enter all the negative numbers first. So you would enter, for example, -24, -12, -8, and so on. And then you would follow by entering your positive zeros. So I have a long list here. Again, I always start with 1. Hopefully that works. So 1, if you notice, if I do the work, it doesn't work. So then I go to -1. I probably tried -1 and that probably didn't work. So then I went to 2 and 2 probably didn't work. So I went to -2. So I bring down the 9 times -2 is -18. And if we keep doing the work, then we'll see that we get 0. So that tells me that x equals -2 is a 0. So if I look at my quotient here, since I had x to the 4th, I'm going to start with x cubed. So now we're going to get 9x cubed minus 27x squared minus 4x plus 12. So usually at this point, we were able to use the quadratic formula or we were able to factor. But the problem here is that your quotient is not quadratic, it's a cubic. And so if that happens, then there's all we need to do is run the same process again. So we would find the possible zeros for, the factors of 12, the factors of 9, divide them, and then find the possible zeros. So that's what we'll do here. And so now my list is going to be a little bit different. And then I start synthetic division again. I'm going to use 3 here. So I bring down the 9 times 3 is 27. We get 0. And then we end up with 0. Again, I started with 3. Remember earlier I checked 1 and -1. Those didn't work. So I just want to continue down the list. So now my quotient, since this was cubic, now we're going to start with x squared. So this would be 9 times x squared. And then there's no x. And then your constant -4. Okay. And then that last number is your remainder. So now this is quadratic. So that's a good thing because now we can set it equal to 0 and solve for x. So I'm going to add 4 on both sides, divide by 9. So we get x squared equals 4 ninths. Take the square root. So the square root of 4 ninths is going to be 2/3. It's plus or minus 2/3. So if we write down our zeros, then we have that x equals -2 as a 0. And then the other zeros are x equals 3, since we got a 0. And then we get the 2/3 and the -2/3. So we have 4 zeros. Our degree is 4. And so that is going to be our zeros. And then the factors, if you wanted to find the factors, then x equals -2. If we bring the number to the left side, we get x plus 2 and so on. We'll use the factors in a little bit. So now let's put one problem all together with everything that we did in the previous sections. So first, we want to list all the possible zeros. So we're going to do that. So this is, let me just check really quick. All right, so our possible zeros are 1, 3, and 9. If we use synthetic division, then we get 0, so that's good. And then we set it equal x squared minus 9 equals 0 and solve for x. And I think we did this one earlier, but the reason I have it here is because we're going to end up graphing it. Okay, so the first 2 steps were done previously, and I just wrote them here for us to look at them again. Now we want to sketch the graph. So to sketch the graph, remember you have to know the end behavior. Does it rise to the left, fall to the right? Does it rise on both sides? What does it do? The multiplicity of the 0, which is going to tell us if the graph is going to touch or cross at that 0. And then, of course, we need the zeros, which are right here. And then the last one is the y-intercept. The y-intercept is whenever x is 0. So if x is 0 here, and x is 0 here, and x is 0 here, then our answer would be -9. So if the problem is set up this way, then your y-intercept is always your constant. Okay, so just to break it down further, if you want to get the behavior, this is our polynomial. The degree is 3. That means that it's going to behave like one of these 2 here. And then the leading coefficient is positive, so it's going to behave like this graph. So we're going to say that the graph rises to the right and it falls to the left. Okay, here are my zeros. So I have these 3 zeros. None of them are repeated an even number of times. Therefore, my zeros are going to be crossing. Okay. And then last, the y-intercept, as I mentioned earlier, we let x equal 0 and solve for y. So we get -9. So that's going to be your y-intercept. And then the last step is to pick additional points. But I encourage you to do those after you graph the information that you do have. So the first thing I would do is I would plot my zeros. It's not going to show the picture. Let me go back. And let me get my pen. And so let me just draw it on this same thing here. Okay, so your zeros are -3 and -1 and +3. Okay, so the first step is I would plot my zeros. Then I would apply my end behaviors. So at this 0, I know end behaviors. So at this 0, I know that the graph is going to rise to the right. And I know that at x equals 3, the graph crosses. So I'm just going to do something like this. And then on the x equals -0, the graph is going to fall. So it's going to go something like this. Okay. So in order to fill in the gaps in here, we need to plot additional points. So the additional points that I would encourage you to use are the ones in between the zeros. Because if you get a point out here, then that's just going to be up here because the graph is going to come this way. Okay, so let's go on to the additional points. So I chose -2 and +1 and +2. And so if I was to plot everything, then the graph would look something like this. Okay. And then the last one that I should have graphed earlier was your y-intercept of -9. So at -9, it's going to cross it there and come back up. Okay, so that was taking everything that we did and put it together to make one graph. Now we're going to go a little bit backwards. It says find a polynomial function with real coefficients that has the given zeros. So by finding a polynomial function, what they want us to end up with is going to be something like this. X cubed plus blah, blah, and so on. Okay. So that's what we're trying to find. So one of the things that they do here is they give us 2 zeros. So again, our goal is going to be to end up with a polynomial that looks like this one here. They tell you that x equals 3 is a 0 and x equals -4i is a 0. So whenever you have an imaginary 0, its conjugate is also going to be a 0. So there's actually 3 zeros here. So the other one is x equals 4i. So I have 3 zeros. So this would be a degree of 3. So your next step is to take your zeros and list the factors. So for x equals 3, I get x minus 3. For x equals -4i, I get x plus 4i. And then x equals 4i, I get x minus 4i. So we're going to set these as a polynomial function. So I can write it as f of x is equal to an. An is just, we're not sure what the leading coefficient is right now. So we can just write it as an. Okay. So next, we're going to write our factors. So the first factor is going to be x minus 3, followed by x plus 4i, x minus 4i. So what I like to do is I like to multiply the imaginary numbers first. So I get x times x is x squared, x times -4i is negative 4ix. 4ix is 4ix. And then 4I times negative 4I is negative 16I squared. Now I squared is the same as negative 1. Okay, so instead of I squared, I can write it as negative 1. And then negative and negative is going to be positive. So we can write it as x squared plus 16. Now I'm going to multiply x times x squared is x cubed. X times 16 is 16x. Negative 3 times x squared is negative 3x squared. And negative 3 times 16 is negative 48. Gather up any like terms that you have. And I like to write them in descending order. So I have x cubed minus 3x squared plus 16x minus 48. So in this problem, they don't give us any other information. So for an, you can use any number. We can just use 1 for now. So if I have a 1 and I multiply it into the parentheses, then I'm going to end up with the same information. So that would be your answer. Later, and I think it's the next slide, we give you information so that we can actually find out what the an is. Okay. So for this example. So here we have degree 4, negative 4, 1, and I are zeros. So if it's degree 4, we should have 4 zeros. So since I is a 0, then negative I will also be a 0. So I include it as part of my zeros. We get our factors, and then we set it up. So we're going to multiply our factors, our imaginary numbers first. X times x is x squared. Ix and negative ix is going to become 0. And negative I times I is negative I squared. Simplify a little bit. And now instead of I squared, I can write it as negative 1. So we get negative, negative. That's going to be positive. And now I'm going to multiply this. X times x squared is x cubed. X times 1 is x. Negative x squared and negative 1. And then we're going to need to multiply times this one here. So x times x cubed is x to the 4th. X times x is x squared. X times negative x squared is negative x cubed. X times negative 1 is negative x. 4 times x cubed. 4 times x. 4 times negative x squared. And 4 times negative 1. Now we need to gather our like terms. So we get x to the 4th. I have an x squared and a negative 4x squared. So that's going to be negative 3x squared. And then 4x cubed minus x cubed is positive 3x cubed. And then we have 4x and negative x is positive 3x minus 4. So that was a lot of info. But now, instead of just using 1, they give us something called the solution point. And in this solution point, we have f of 0 is equal to 8. So 0 represents x, and negative 8 is your y. So what we can do is, in my x's here, I can replace them with zeros. So 0 to the 4th, 0 cubed, 0 squared, and so on. And I know that this whole thing is equal to negative 8. So if we simplify in here, this is 0, 0, 0, and 0, we end up with negative 4. And so now I can divide by negative 4. And so negative 8 divided by negative 4 is going to give me a positive 2. So I'm going to go ahead and write that in the front here. And then I'm going to multiply everything by positive 2. So my answer is 2x to the 4th plus 6x cubed, and so on. Okay. So now we'll do a little bit of 2.6. So 2.6, they give you a rational function. The first thing is to get the domain, the x-intercepts, and then the asymptotes. So let's break it down. So for the domain, remember that the function has a fraction. So there are some numbers that are not part of the domain. So to find those numbers, we set the denominator equal to 0 and solve for x. So when we solve for x here, we get x equals -3. That means that your domain is all real numbers except for -3. And so that would be our last option here. The the x-intercept, we set y equal to 0. And so we have, let me go ahead and replace it with 0. Then we're going to multiply by x plus 3 on both sides. And so we get 0 is equal to 1. So that's a false statement. So that means that there's no x-intercept. Now for the y-intercept, we let x equal 0. So if I substitute 0 for x, I get 1/3. So that's my y-intercept. Now the vertical asymptotes, these are the steps to finding it. First, you want to factor the numerator and the denominator. And then we're going to set the denominator equal to 0 and solve for the variable. If you happen to cancel a factor, then you're going to have a hole in the graph. So here's my example, right? So I'm going to factor both the numerator and denominator. They're already factored. There's nothing more I can do there. Set the denominator equal to 0. So x equals -3 is a vertical asymptote. And we represent those with a dotted line through x equals -3. For the horizontal asymptotes, there's 3 cases. If the degree of the numerator is less than the degree of the denominator, then your horizontal asymptote will always be at y equals 0. If the degrees are the same, then you have to divide the leading coefficient of the numerator divided by the leading coefficient of the denominator. And then the last situation is if the degree of the numerator is greater than the degree of the denominator, then there's no horizontal asymptote. But there could be a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. So let's find the horizontal asymptote for this problem. So the degree of the numerator is going to be 0 and the degree of the denominator is 1. Okay, so that means that the degree of the numerator is less than the degree of the denominator. Therefore, there exists a horizontal asymptote at y equals 0, which I represented here with this horizontal dotted line, which happens to be the x-axis. Okay, so far we have that information, and the last step is to graph it, and you will need additional points. So first, let's graph everything that we have so far. So we have our vertical asymptote at x equals -3. Our horizontal asymptote is the x-axis. So we don't have to graph it since it's the x-axis. My y-intercept is at 0 and 1/3. And that's all the information I have. So if you're not sure what to do here, then that's where we need to pick additional points. And so the additional points that I'm going to choose, some are going to be on the right side of the asymptote, and some will be on the left side. Okay. So I'm choosing -2, and then I'm choosing 2. And I'm going to choose -4 and -5. And so if I plot those points, then we have this point here, which is 1/5. Then we have our y-intercept. Then we have our 1. And then for -4 and 5 is down here. So the graph looks a little weird, but all the rational functions kind of behave the same way. So the asymptotes just tells us that the graph is going to get closer and closer to that asymptote, but not past it. And so I can draw this, and that's going to keep going up forever. And then this will keep going down this way. It's not going to touch it because the x-axis is already an asymptote. And then we have to look at the bottom one here as well, which will have the same behavior. So let's do this next one. So we have cx is equal to 3x plus 2 and divided by x plus 3. Okay. The domain, there's a fraction, and so we set the denominator equal to 0. So our domain is going to be everything except for -3. Okay. The x-intercept, we let y equal 0. So we're going to multiply both sides by x plus 3. So we get 0 is equal to 3x plus 2. Subtract the 2 and divide by 3. We get x equals -2/3. And then for the y-intercept, we let x equal 0. So we get that the y-intercept is 2/3. So they should say y equals 2/3, not the x. It's y equals 2/3. Now for the vertical asymptotes, we want to check if we can factor. This is already factored. So we set the denominator equal to 0, and we get x equals -3 is going to be our vertical asymptote. Our horizontal asymptote, notice that the degree is 1, and the degree here is 1. So we're going to divide them, and we get 3 divided by 1 is 3. So my horizontal asymptote would be at y equals 3. So if I plot what I have, we have -2/3 for our x-intercept, and then we have our 2/3 for the y-intercept. I'm going to pick points on the right side of the asymptote and the left side. So I use -2, 2, -4, and -5. So if we plug in those points on our graph, then we can see that the graph will behave in this way. Okay, and then I have this last one. It's similar, x squared minus 9 divided by x. If we look at the domain, it's going to be everything except for 0. If we solve for the x-intercept, we're going to let y equal 0, multiply by x on both sides. So we get that x equals plus or minus 3 is our x-intercepts. And then for the y-intercept, we get 0 minus 9 is 0, divided by 0. We cannot divide by 0. So the y-intercept does not exist. And then the asymptote, so factor both numerator and denominator. So we have x minus 3x plus 3. There's nothing I can cancel. So my vertical asymptote is x equals 0. My horizontal asymptote, this is the degree is greater than the denominator degree. Therefore, there's no horizontal asymptote. And the degree is 1 more than the degree of the denominator. So there's going to be a slant asymptote. How do we find the slant asymptote? So to find the slant asymptote, we're going to go ahead and take the divisor. So notice that we have x. So we have x minus 0. So 0 is your divisor. Bring down the 1. And we get that our quotient is going to be x. So the equation of the slant asymptote is just y equals x. And if you were to graph it, it looks something like this. So we have these points here. My slant asymptote is going right through the middle. And if I pick these additional points, then when I graph it, it will look something like this. Okay, so I think we're not going to have time for the next section here, but I wanted to include it. That way, if you want to go through these examples from 2.4, right here where my mouse is pointing, you can click that arrow pointing down with the box around it, and you can download the PowerPoint. Okay, so I'm going to go ahead and pass it over to the staff, and then that'll be it for today.
Thank you, Ms. Chuka, for your wonderful presentation. We do want to remind you all about the previously recorded sessions, which are available on a YouTube playlist. Today's session will also be available on the playlist later today. Also linked is a short survey to help us improve our TVE sessions. Please take time to fill out the survey. Before you leave, I want to share the TVE sessions that we will have next week for Happy Math Hour. Where Math 1314 will be covering the exponential and logarithm functions, part 1. Math 1324 will be navigating your course and exam 1 review. At 1 p.m. today, we will also have Student Success presenting reading workshop with Rose Galindo. Thank you all for coming in today. We hope you all have a lovely weekend. If you have any questions, feel free to use the chat box or the mic. We hope to see everyone again for Math Happy Hour. Have a great weekend.